Welcome, agents. Today, we are initiating a targeted extraction on one of the most notoriously tricky topics in your Cambridge 9702 physics syllabus, uniform electric fields. If you have ever found yourself staring at a past paper, wondering how on earth to calculate the exact trajectory of an electron fired between two parallel plates, you are in exactly the right place. We are going to decode the mechanics of uniform electric fields and give you the strategic blueprint to extract maximum marks whenever this topic pops up. Let's get right into it.
Here is your mission briefing and roadmap. First, we'll establish our baseline by defining field strength. Second, we'll zero in on the uniform field environment. Third, we'll crack the math behind parallel plates. And finally, the ultimate payload, tracking particles in motion.
Section 1. Defining field strength. To conquer this topic, we need to master the foundational intel, the field itself.
All right, let's break down this core concept. Electric field strength, which we represent with a capital E, is defined simply as the force, F, exerted on a charge, Q, located inside that field. The formula to lock into your memory is E equals F divided by Q. Rearrange that and you get F equals QE. Now listen up, because here is a classic trap where students lose easy marks. Do absolutely not confuse this capital E with energy. They both use a capital E, but here we are strictly talking about field strength. Since force is in newtons and charge is in coulombs, our standard unit is newtons per coulomb. Before we continue, subscribe to our YouTube channel Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Moving on to Section 2, the uniform field. Let's shift our focus from abstract, messy fields to a highly specific, carefully controlled physical environment.
Enter the uniform field. By definition, a uniform field is a region where the electric field strength is exactly the same at all points. What does that mean for your exam paper? It means predictability, absolute consistency. In this special type of field, the force experienced by a specific charge is completely identical no matter where it happens to be placed within that zone. Top, bottom, dead center, the field pushes or pulls with the exact same intensity everywhere.
So how do physicists actually build this controlled environment in a lab? And more importantly, how do you draw it for the examiner? We use two charged parallel metal plates, positioned a certain distance apart, literally just a basic parallel plate capacitor. When you sketch this, you must draw the electric field pattern as parallel, equally spaced lines running straight from the positive plate to the negative plate. That equal spacing is your visual shorthand to tell the examiner, I know the field strength is constant here. The only exception is right at the very edges of the plates, where the field lines bow outward slightly, known as the edge effect. But in the center, perfection.
Section 3. The math of parallel plates. We have our controlled environment, so let's transition into the numbers and see how we actually calculate the electrical forces acting inside this setup.
Stop scrolling, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, let's look at one of the most elegant derivations you'll need to know. Imagine a positive charge resting on one plate, and we want to move it. Standard mechanics tells us work done equals force times distance. But electrical physics tells us work done is also potential difference, voltage, times charge. Because work is work, we just set these two equal to each other. F times D equals V times Q. Rearrange that, bring in charge to one side and distance to the other, and boom, electric field strength E equals voltage V divided by distance D. It's a beautiful link between mechanical work and electrical potential, and a massive point earner.
Now, this derivation gives us an incredibly useful strategic advantage, a brand new unit of measurement. Earlier, we said field strength was measured in newtons per coulomb, but our new equation, voltage over distance, gives us volts per meter. The secret here? These are perfectly equivalent SI units. Cambridge examiners love to switch between these two to test your confidence. Don't be fooled. Whether a question gives you newtons per coulomb or volts per meter, you are looking at the exact same physical property.
A quick strategic side note here. Our E equals V over D equation assumes the potential difference drops at a constant, steady rate over the whole gap. But if you encounter a scenario where it varies, no sweat. We simply adapt the formula to look at a small change in voltage, delta V, over a small slice of distance, delta D. It's the exact same core concept, just zoomed in to look at the gradient.
Finally, Section 4, Particles in Motion. We've defined the field, drawn the plates, and locked down the math. Now let's drop a particle into the mix and watch the sparks fly.
Think about this dynamically. We have an invisible, totally uniform force field. We introduce a tiny, charged mass. What physically happens to that particle when it enters this highly structured environment? This is where you really get to flex your physics muscles.
The particle's trajectory completely depends on its angle of entry, and examiners will test you on two specific scenarios. First, imagine a particle entering the field perfectly parallel to the field lines, or just released from rest. Because the force is pushing perfectly straight, the particle simply accelerates in a straight line, picking up speed. A positive particle goes with the field, a negative one goes against it. But scenario 2 is the fun one. If the particle enters perfectly perpendicular to the field lines, say flying horizontally between the plates, the electric field exerts a constant force at a right angle to its motion. The result? A curving parabolic path, exactly like a ball thrown horizontally off a cliff.
Speaking of throwing a ball off a cliff, you might be thinking, hey, what about gravity? Here is a critical piece of exam strategy. When calculating the paths of subatomic charge particles in these fields, you almost always cross gravity right out of your equations. Why? Because the electric force is staggeringly massive compared to the absolutely tiny weight of something like an electron. Gravity's effect is completely negligible here. If the exam asks you to state your assumptions, writing weight is negligible compared to electric force is a guaranteed mark.
Let's see how all this builds into our ultimate conclusion. Because the field is uniform, the force, and therefore the acceleration, is totally constant. This means we can unleash the classic kinematic equations you learned in mechanics. We take our electric force, plug it into Newton's second law, so acceleration equals QE over m, then drop that right into our standard uniform acceleration equation, v squared equals u squared plus 2as. If the particle starts from rest, initial velocity is 0. Following the steps on screen, we arrive at a beautifully simple result. Final speed depends entirely on voltage, charge, and mass. The macromechanics perfectly predict the subatomic world.
Which brings us to the ultimate shortcut. You can bypass kinematics entirely and find that exact same final speed by looking purely at energy conservation. The work done by the electric field converts seamlessly and directly into the kinetic energy of the moving particle. V times Q equals 1/2 mv squared. Electrical potential essentially powers mechanical motion. That single equation is the secret weapon for dominating these questions. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCS and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.